Hello everyone, thank you for joining us today for this webinar titled Improving the Fire Reaction and Fire Resistance Properties of Composites. It is brought to you by Composites World and presented by Technical Fiber Products, TFP. My name is Ginger Gardner and I am Senior Editor at Composites World. Advanced composites are increasingly used in applications where they need to meet stringent fire resistance requirements. TFP's nonwovens enable composites to pass fire test standards and have been used extensively in infrastructure, construction, mass transport, and aerospace applications. This webinar will discuss TFP's Technifier product, which has been used to pass key fire resistance standards, including ASTM E662, E162, and the rail standard EN45545. This webinar will show how Technifier is easily incorporated directly into a composite, protecting the structure from fire while reducing smoke and heat release. The webinar will also present new fire resistance test data. Primary topics include an introduction to the Technifier product range and how it provides fire protection for composites, how Technifier can be combined with FR resins, and how it integrates into FR laminate composite assemblies, and a range of case studies highlighting the use of Technifier in composites applications. Our presenters today are Neil Gray and Scott Klopfer. Neil Gray is TFP's Business Development Manager. He has a degree in chemistry and an MBA, as well as 25 years of experience in the composites industry in both commercial and technology management. Neil has held a range of R&D and business development/management roles with a key focus on fire, smoke, and toxicity, FST, performance systems. Neil sits on both the Composites UK Construction FST Working Group and the BSI Reaction to Fire Testing Committee. Scott Klopfer is the Composites Fire Protection Specialist at TFP. He has a BS in Chemistry from SUNY Fredonia and has worked in the composites industry for 10 years. Scott plays an active role in the U.S. fire protection community, acting as committee chair for the PINFA-NA organization. Before we begin, I'd like to remind you to please submit your questions by typing them into the question pane on your control panel at the right of your screen. We will answer these during our Q&A session at the end of this presentation. And now I'm going to hand it over to Neil and Scott.
Thanks, Ginger, and thank you to Composites World for the opportunity to present this webinar today. Good afternoon or good evening, everyone, and thank you for your attention. The title of the webinar is Improving the Fire Reaction and Fire Resistance Properties of Composites. And this is what Scott and I are going to be covering over the next about hour. So we're going to start by looking into what do we actually mean by reaction to fire and fire resistance. So how do they differ and how are they measured? We're going to have a look at the fire triangle and how to disrupt it. How can we prevent composites from acting as a fuel source in a fire? Scott is going to introduce the Technifier range of intumescent veils, and we're then really going to drill down into some recent projects assessing the performance of Tecnofire intumescent veils in terms of fire resistance results and reaction to fire results. We're then going to look at some real-life composite applications and case studies where Technifire finds application. We're going to sum up some new developments, then end with some conclusions and some Q&A. So what do we mean when we talk about reaction to fire versus fire resistance? Reaction to fire is the measurement of how a material or system will contribute to the development and spread of a fire, particularly in the very early stages when evacuation of personnel may be crucial. So it's, does a material burn? How quickly does it burn? How much heat does it liberate? Fire resistance is the measurement of the ability of a material or system to resist and ideally prevent the passage of fire from one distinct area to another. So this is really looking at the ability of a composite material to retain its structural integrity in a fire event, to retain its mechanical properties. And both of these definitions are courtesy of Composites UK. So this is a really elegant hexagonal understanding fire diagram that nicely sums up how we assess the performance of composites in terms of reaction to fire and resistance to fire. So if we look at reaction to fire, the sort of parameters that we're evaluating, the sort of testing that we need to do is to look at the time to ignition, the flame spread, and the heat release rate. So does the part burn? How much heat does it liberate? In terms of resistance to fire, we're looking at the structural failure. Again, how well does it retain its mechanical properties? Does it liberate any burning droplets? And that then leaves the combustion products, the toxicity, and the smoke. And that diagram really encompasses FST overall: fire, smoke, and toxic fume. And I've got to say thank you to our friends at Finesta Coatings in Finland, who we do a lot of work with, who have very kindly allowed me to share this, what I think is quite an elegant diagram to understand this area. So let's have a look at the fire triangle, which I'm sure you've all seen before. So if you have a fuel source in the vicinity of heat and oxygen, that can lead to a chain reaction that can lead to a self-propagating fire. And to put that fire out, you need to remove one of those three levers. So you need to either take away the fuel, the heat, or the oxygen. So what strategies are available? How can we stop composites acting as a fuel source? Because composites will burn. The resins that composites are based on are generally based on hydrocarbons. So how do we prevent composites from acting as a fuel in a fire? We can incorporate halogen and antimony systems, which deactivate the free radicals in the flame front. So the flame is actually a free radical reaction. We can incorporate mineral fillers that liberate water or inert gases under the action of heat during the fire. So compounds like aluminium trihydrate that liberates water. We can incorporate additives or mineral fillers that react endothermically to remove energy from the fire. So in the fire, they break down by absorbing energy, so they take energy out of the fire. However, all three of those aspects have negative potential impact. The halogenated systems liberate toxic fumes. The middle two utilize high levels of mineral fillers, which have a negative impact on weight and on mechanical properties. And as we all know, one of the main applications and drivers for composites is their advantageous mechanical property to weight ratio. But there's a fourth route that can be employed to prevent composites from burning, and that's to incorporate technologies or products that form a stable char layer on the surface of the composite during the fire event. So this could be an intumescent paint coating, a gel coat, or an intumescent veil. So under the action of heat, these products intumesce or swell, expand to form a stable char layer, often a carboniferous char layer, that effectively insulates the backing laminate and protects it from the fire. And there's two real advantages in terms of the char layer approach. One is that it doesn't offer any of the disadvantages of the above strategy, so you're not generating more toxic fumes, there isn't a negative impact on weight or mechanical properties, and it actually acts on all three levers of the fire triangle. So that stable insulating char layer reduces the oxygen and heat from getting through to the backing laminate and reduces any fuel source that's liberated in a gaseous form to leaching out into the flame front and acting as a fuel source. So I'm now going to hand over to Scott, who's going to introduce the Technifier range of intumescent mats and veils. Over to you, Scott.
Thanks, Neil. I just wanted to first introduce Technical Fiber Products. We are a non-woven manufacturer. We use a wet lathe process to manufacture non-wovens. Essentially, it's a paper making process, a bit advanced, where we use fibers such as carbon, glass, thermoplastics, and we do offer a range of this intumescent product called Technifier. It's a very customizable product. Basically in a wet lathe process, you're going to mix together a batch of different components and then spill those across a moving wire to dry them out, and you end up with a fabric, a rolled good. So we have the ability to add different fibers and particles into that mix, or look at some different active ingredients, some FR materials. ATH, as Neil referenced earlier, is one of those materials that we can add into our product. We make a few different forms. If you look at that picture on the right, that would be the form that comes off our paper making machines, our non-woven machines. It's more of a fabric. There are flexible and rigid forms. This would be the flexible form. We also offer a rigid form, which is kind of like a pre-preg. We've added an epoxy resin system to it, and the end result is going to be a veneer type Technifier. So very more of like a scratch proof surface than a fabric itself. We offer the rolled fabric on a 50-inch maximum width. The length of that can differ depending on which weight or which thickness you choose. We can cut these into sheets or even shapes. We offer this in narrow coils, so 50 inches are max, but we could also give you down to quarter or half-inch wide roll. The idea behind an intumescent is to have a product that does create that false wall, that char layer, once it expands. So ideally, you want to have a completely inorganic fabric, but we have to use a bit of a binder. That's the only organic component. The binder is necessary just to keep the product together and also survive processing. Next slide, please. So the Technifier expands, as Neil had pointed out. If you look at the graphic on the right, we're going to be activated. That expansion will begin around 190 C, 374 degrees Fahrenheit, but not much is going to happen at that level. Once we see a larger amount of heat, a higher flux or a higher amount of heat into the system, you will see that expansion. If you can see, the middle graphic is a 250 C and then up to 400 C. Realistically, the full char layer is in that 400 C range. It's going to expand directly at the heat source, not just necessarily flame, but it's a Z plane only. So it's going to directly, react to the flame or the heat that's coming after it. It is irreversible. Once we expand, it doesn't shrink back. The hope is to have a very exceptionally stable char. That's what you need to survive the fire event. As you have air blowing, vibrations, different components of a fire, that char layer staying intact is very crucial. So we do have a product that does end up with a very stable char layer to keep your structure protected. We offer this in different thicknesses. Generally speaking, 0.5 to 2.0 millimeters is our sweet spot, but we can go down to 0.25 millimeters and actually even up to about 9 millimeters thick. Next slide, please. So Technifier has been used in composites. It's 20 plus years now. There is a graphic on the right showing a laminate breakdown of a composite bus. Technifier will generally want to be on the outside to encounter the heat before it can get to that structure towards your core or any underlying materials. If it's covered with a gel coat or a paint, that should be fine. I've even seen applications where they've had a layer of, say, a woven glass on top. We will expand underneath once that heat penetrates. But we are trying to protect an underlying structure. So towards the outside is the rule of thumb. Now, the gray fabric type material you saw earlier is what we call the infusible grade. So that is ready to be infused with resin. It's around 80% void of air, so it will readily accept a resin. Nonwovens are very commonly used as a breathable layer within a composite to assure a proper wet out. So they do soak up the resin. You want to keep that controlled because resins are usually a source of an organic flammable material. So 30 to 40% is what we're shooting for. In terms of what types of processes, it's a great match for pultrusion and infusion processes, vacuum, even hand layup, linear laminates, and also resin systems. We've got a lot of experience behind us with different resin systems, including your FR resins, but even vinyl esters and polyesters and some of the more less expensive market grade composite resins. We do have the ability to raise the initiation temperature up to 250 C. It cannot be lowered, but the 250 C is very suitable when you think about polypropylene processing and hitting temperatures above our 190 C level. Next slide, please. So I'm going to describe some testing and results of the fire resistance testing we've undergone. We're going to start with two different programs in the aerospace industry. The first one, next slide, please. The first one was a study from Aachen University. It's a German university. They were looking at an electric powertrain, so substituting batteries in for the power system. And that battery system would be located on the wing. Next slide, please. So the goal was to design a composite panel type that was load carrying and also lightweight, but that has to include a fireproof component as well. So it's a pretty big challenge when you think about the materials that would be used in its, in terms of structure and your steels, your titaniums, and a lot of the aerospace industry standards. So they looked at 4 different fire protection options. One was an aerogel textile, an intumescent paint, and then the Technifier, which would be an intumescent textile. They looked at a combination of the aerogel and the intumescent paint. These were carbon fiber and epoxy resin plates, panels, and they ran some fire resistance testing at CS23, which was defined as having a survival of 1100 C, or over 2000 degrees Fahrenheit for 5 minutes. Next slide, please. So we're going to look at some breakdowns of some photos on this next slide, where you can see the test mechanism, the test setup on the right, which that CFRP plate is located, and there's a flame impinging from the bottom. Now we're trying to measure the cold side temperature on that plate, and the thickness criterion was to isolate these panels where they're exposed to an 1100 C flame, but the cold side temperature, the critical temperature, would be 80 C. So we can't rise above 80 C. That would be considered a failure. You've now reached the glass transition temperatures of the resin systems and some of the components that will break down and degrade. If you look at the photos, the panels after testing photo on the bottom right, you can see the blank, the unprotected. The next would be an aerogel textile. Then they also used our product as both a dry form intumescent textile and with a resin system. They looked at an intumescent paint, and the last photo was the combination of the aerogel and the paint. They were really shooting for a very low thickness of material to survive that critical 80 C temperature range. Next slide, please. So what they concluded, or what they found from the results, if you're looking at that graph on the left, the x-axis, you'll see a dotted line above that running horizontally. That is that 80 C critical temperature range. And the second line from the left, the dotted line that runs vertically at a slight angle, was the Technifier result. Now, if you look at the chart on the right, it breaks down the 4 materials. It's listed by the isolation thickness and also the surface weight. Now, keep in mind, it's a fairly low density material, our dry intumescent textile. So even though it starts at 9.35 millimeters thick, that can compress quite readily. So very, very commonly through processing, Technifier will be reduced to 1/3 of its original thickness. But the key takeaway was the fact that the intumescent textile with a surface weight of 1.87 kilograms per square meter seems to have the lowest mass and thus promises the best lightweight potential. So Technifier, because of how light it was in the scenario, to protect to that critical mass temperature, it was the choice from this study. Next slide, please, Neil.
Thanks, Scott. So staying on the theme of fire resistance testing, I wanted to give a very brief summary of a study that was undertaken and published in the Journal of Polymer Testing last year. So the title of this paper was Bench Scale Fire Stability Testing, an Assessment of Protective Systems on Carbon Fiber Reinforced Polymer Composites. And really the rationale behind it was investigating methods for improving the ability of CFRP structures to retain their mechanical properties, especially compressive strength, during a fire. And this was driven by the need to improve fire resistance of CFRP in EV aerospace applications, so in the case of thermal battery runaways. So it dovetails nicely with the paper that the study that Scott has just summarized. So let's take a look at what was actually investigated during this project. So CFRP panels were prepared using vacuum-assisted RTM with an epoxy resin with and without a Technifier layer on the surface to assess their potential improvement in fire stability. And I think it's fairly well known that CFRP panels, CFRP composites can retain a reasonable proportion of their tensile properties at elevated temperatures due to the stiffness of the fiber, but they tend to fail under compression very, very rapidly once the resin hits its glass transition temperature. Again, as Scott alluded to, with a T critical in the Arkan study. So for this study, The CFRP panels were manufactured. The ultimate compressive failure load was assessed at ambient temperature. A second set of panels was then fabricated, and these panels were put under 10% of this ultimate compressive load to failure, and the panels were subjected to direct flame of a fully developed fire. And this was a really severe thermal event. It was about 175 kilowatts. If you think that cone calorimetry testing, which is quite an extreme test, is undertaken at 50 and 25 kilowatts. So this was really hitting these panels with a fully developed fire. And the time to compressive failure under these conditions was measured and compared. So if we look at the table on the left, you can see from the control panel, it's failed after 17 seconds under compressive load. So the panel has been put into this severe fire event under 10% of its ultimate compressive load very, very rapidly. The panel has exceeded the glass transition temperature of the epoxy resin used in the composite. That resin has no longer been able to transmit the stress on the fiber, so that the panel has failed under compressive load. If we look at the impact of incorporating the 0.5 millimeter layer of E20 Mi, you can see that time to failure has been increased to 125 seconds. And through incorporation of the 1 millimeter, the E10M mat, that's been further increased to 176 seconds. So the Technifier has improved the fire stability, and fire stability really is an interchangeable term with fire resistance, by up to 1,000%. And hopefully from the description that Scott gave about how Technifier works, about the way that when the material, the veil, hits its activation temperature and swells or intromesses to form that stable insulating char that's protecting the backing laminate, you can conceptualize how that stable char is insulating, protecting the backing laminate, and allowing it to survive, allowing it to retain its mechanical properties, its compressive strength for a longer period of time. The temperature at failure was also measured. The control panel failed, not really surprisingly, at 89 degrees C. Again, the glass transition temperature of the epoxy resin, and this is why the T critical in the Arkan study that Scott mentioned was set at 80 degrees, so the panel couldn't exceed 80 because of this very aspect. Again, if we look at the 0.5 millimeter E20 Mi, you can see that temperature at failure on the surface of the panel has been increased to 142 degrees C. The E10M mat, the 1 millimeter, has increased that to 155. So again, hopefully you can visualize the way these materials, these intromescent veils, are expanding, giving us that stable carboniferous char that's insulating and protecting the backing laminate and allowing it to survive at a higher temperature for a longer time. And the presence of the Technifier has almost doubled the temperature the panel could withstand before compressive failure under load. As I'm sure you can see that in an aerospace application, if you have an EV battery runaway, being able to retain the mechanical properties of the CFRP for as long as possible is absolutely critical. As a quick aside, we are going to be presenting quite a lot of data during this 1 hour webinar in terms of external academic papers, in terms of external research programs and external testing programs. We can only do that at a very, very high level. What we'd really like to do for interested parties is to send you copies of these papers so you can assess them in a bit more detail, discuss them in your teams, and then set up a meeting, a call after the webinar so we can discuss in more detail how these results could be applied to your applications. So I'm going to hand back to Scott now. We're going to move from looking at fire resistance to reaction to fire testing. And Scott's going to sum up some recent results to ASTM 162, 662 and some E84 data. I'll then pick up the presentation again to talk about the EN standard. Over to you, Scott.
Yep, thanks, Neil. We're going to break this into 4 sections, as Neil pointed out. We're going to start with the ASTM E162. Next slide, please, Neil, which is a transportation requirement for fire testing. Next slide, please, Neil. So the 162 test is a flame spread test. Very commonly, fire testing comes down to some reaction to flame, meaning a flame spread, and also looking at the smoke generated. So there are two unsurvivable situations usually when there's the fire event. So the reason behind running 162, surface flammability of materials, is to help manufacturers meet those safety standards in the construction of buses, trains, recreational vehicles. The 162 is a very, very common, it's more of an indicative type test to learn how flames spread across a material. So a composite panel was designed in this experiment with some very common components I'll discuss in the next slide. But if you look at the picture on the right, you can see the test setup itself. There's a radiant panel that's giving off an amount of heat and also an acetylene pilot flame that is hitting the backside of your sample, which is in a 30-degree vertical position. So what we're really looking to do is measure how far that flame runs from the pilot down your specimen. So the purpose is to determine the relative surface flammability performance of different materials under these conditions. The results are recorded as a flame spread index. Next slide, please, Neil. So very commonly in construction, architecture, trains, there are panel systems. So we've looked at trying to design a market-led panel, a generic panel for the industries to look at. And we've chosen 3 different samples to run where you can see how we've increased the fire retardancy from sample 1 to sample 3. Sample 1 was the standard industry ortho resin, 2 layers of a continuous filament mat, a glass mat. In sample 2, we added a 1 millimeter Technifier that does contain the ATH powder. And in sample 3, we went with a high performance flame retardant resin, plus those other layers already mentioned. So we've scaled up in complexity from sample 1 to sample 3. I won't break down every number, but you can see as we've gone from the single control through to a full systems approach, we've reduced that flame spread factor significantly. The average heat of evolution as well was reduced down almost in half, and then less than that in the systems approach. And the key to this test really is that LS, that flame spread index, which started at 165 for the blank and ended up at only 30. The bar chart on the right just summarizes those 3 different measurements. Next slide, please, Neil. So one thing I did want to point out before I forget, because these panels were also used in a 662 test, the resin we use, the high performance flame retardant resin, generally would want about a 200 parts per 100 loading of ATH into the resin, the filler. We were able to scale that down to 65 parts. So you can think about the viscosities and the throughput in an end part, what effect that would have. So we also ran a 662. Now 162 and 662 make up what's called document 90, which is a test requirement in the transportation field. A lot of times you'll see that in the States in rail and bus designs. So these 2 combined make up the Doc 90. So next slide, please, Neil. The 662 is a optical density smoke test. So how much smoke is generated when you have a composite part once it sees some flame or some heat. The flammability test is usually construction materials, plastics, and coatings. And like I said, you're looking at it's an opacity measurement. So you have an eye that is seeing the smoke cross through a laser beam and reporting back how much obscuration of that beam is registering. So we're very commonly seeing coatings, construction products, materials, and textiles being screened out using tests like the 162 and 662 for the construction industry, the rail industry, and even in the military sector. Again, it's a very small sample in this case. This is only, the other sample size was, it's an 18-inch, I believe 6-inch or 12-inch on the 162. This is a 3-inch by 3-inch, so very small sample sizes compared to E84, which I'll go over next. So it's a radiant panel, heats up at the source, the face of your sample, and then we're going to measure a few different optical smoke densities at 1.5 minutes and also 4 minutes. Next slide, please, Neil. These are the results in the 662 testing. You can see there's a non-flaming and flaming portion of this. So the key takeaway here is after 4 minutes, sample 1 registered a 3.9 in the non-flaming. For the how much smoke was generated, we reduced that down to 0.5. And once this was set alight, the flaming version the blank was at 109.3, and we reduced that down to 0.9. So an incredible change from going from samples, the blank sample to the systems approach. The corrected max specific optical density chart is on the right. The corrected just means that they take into account any solids that have deposited on the optical lens. So you can see the results between the non-flaming and flaming and how much of a reduction we saw. Next slide, please, Neil. I'll summarize both these tests on this slide. So the ASTM 162 panel test that we ran, transit authorities will look at an acceptance criterion of 35 for this flame spread. The Technifier plus the high performance resin panels measured a 30. So we would have qualified for that, which also would have qualified for the DOC 90 in terms of a design. And then the 662, you're looking to specify materials in the transit authorities with a DS of 100 maximum, and at 4 minutes, that was for the minute and a half, sorry. And at 4 minutes, the DS, the smoke opacity of 200. So we reduced down the DS on the minute and a half to 0.4 out of 100, and we reduced the other one down to 0.9 after 4 minutes. So 0.9, when you think about the mass, the maximum allowed is 200, we're really at just a fraction of that. There are a lot of other components that you might bring into a train floor that might add to that. So we are not going to contribute to that. We've also concluded that the systems approach, fire protection performance in this composite panel shows a promise where lightweighting and longevity were critical. Adding multiple components is really the way to go. When you look at some of these harder tests, like an E119, an NFPA 285 or 286 test, the next step would be to just really run the E84, which is another flame spread and smoke test, and then look at other reaction to fire and fire resistance testing. Next slide, please, Neil. So I will go over also some past E84 testing. This would be a kind of construction industry standard, the Steiner tunnel test. Next slide, please. We've run our product autonomously without any other components or resins involved. We looked at, E84 is another flame spread and smoke develop index for interior spaces in the building industry. The IBC, the International Building Code, classes these into 3, A, B, or C. A is what I found in my experience that most manufacturers are looking to pass. The difference between A, B, and C is the flame spread index. The smoke index, the SDI, will remain consistent. Any SDI above that 450 is considered a non-survivable situation. So we're looking at designing, say, a flat panel or some kind of a composite panel that can achieve a Class A. We've also elevated some other programs where people have passed with a Class C before they want to get to an A. And Technifier has enabled that in some cases. We looked at, in this particular test, we looked at 3 different grades of Technifier. Next slide, please, Neil. So the first version in that top chart was C659403. That is a resin infusible grade. That was that gray fabric type material. If you look at the picture below, you can see the before and after. That shows the Steiner tunnel with the top off. So you can see our specimen. It's a 24-foot long by 2-foot wide specimen. And you can see the after effect. So during the test, they're going to run a high heat flux flame from the bottom of the one end of your sample. And there's going to be an open window along the side of the tunnel that a technician will sit and watch to try to see how much of a flame spread is observed in that side of the tunnel. So we actually had a 0 flame spread for all 3 of the Technifiers tested, meaning it never caught fire on the surface of the material. The after looks like it had, but that's what you're seeing there is that formation of that char layer. So that char layer that is built up of some high temperature fibers and also the expandable components has done its job properly, and it didn't allow a flame to propagate. Now, what surprised me, the SDI, the smoke develop index, where again, the maximum for this test is 450. We only developed a maximum, an SDI, sorry, of 5 for the infusible grade. The next 2 grades were the pre-preg type. The one I mentioned before, that's a hardened version where we have an epoxy resin system as the matrix. They only added to that smoke number 15 and 30 respectively. So this still gives you a lot of room, right? We're not adding a lot to the smoke numbers in our materials itself. So we would have achieved a Class A rating for all 3 of those Technifiers. And I believe with that, I'm going to pass it back to Neil. He's going to discuss the EN 45545 rail standard testing that was run. And I'll talk to you at the conclusion.
Thanks, Scott. So staying with reaction to fire testing, does a material burn? I wanted to briefly sum up some results we have, which have recently come to fruition, to EN 45545, which is the European harmonized rail specification. So if we go back to our fire hexagon diagram, which shows the tests that we use to evaluate the key parameters in terms of fire resistance and reaction to fire, this is really useful to look at the three key tests that comprise EN 45545. So the first test is ISO 5659, and that's evaluating the toxic fumes and the smoke opacity produced from the composite when it burns. ISO 5660, which is the cone calorimeter, is used to assess the heat release. How much energy does the part release when it burns? And ISO 5658 is used to assess the flame spread, the surface flammability. How quickly will a part burn in a fire event? So you can see this is a really all-encompassing standard that covers all areas of FST. The F, the fire, is covered with the flame spread, the heat release, and then the S and the T, the smoke and the toxicity, is covered by the 5659. So we wanted to assess the impact of incorporating a 0.5 millimeter layer of a Technofire incandescent veil, in this case E20 Mi, and the E20 expands by 20 times its original thickness when it's activated in the fire event. So we selected three different resin systems to assess in the composite application: a non-FST general purpose orthophthalic resin to start with. We then moved on to a mid-level FST resin, and then finally a high performance, a heavily ATH filled FST resin. And panels were manufactured by vacuum infusion using a typical combination chop strand matte biax glass, and all the panels were post-cured. So all of the panels across all of the different resin systems were equilibrated, were made as equivalent as possible. And the Technifier was incorporated simply as part of the reinforcing stack pre-infusion. So it was dropped in. You can think of it as a functionalized surface veil. The evaluation was undertaken by an external test house, which is Brandhaus in Germany. And I'd like to just acknowledge Tom Kugelstadt at Scott Barder, who helped with the preparation of the panels and pulling the project together. In terms of 45545, the level of performance, the output of this standard, is covered by three hazard levels. And HL1 is the lowest level, HL3 is the highest level. So try to bear that in mind when we're looking at the results. And the hazard levels are defined both by the type of train and where it operates. So for example, a metro train or an underground train operating solely underground in tunnels would be assessed as having the highest hazard level because of the challenges, if there was a fire, of safely getting people off the train and getting them out of the tunnel and into a safe environment. So let's start to have a look at the results. Now I'm only going to present the results from the standard general purpose orthophthalic resin and the mid-level FST resin due to time constraints. Very happy to share the results on the high performance resin outside of the webinar. So if we look at the table in the first column, we've got the four key parameters to this fire specification. We've got the heat release rate. So how much energy does that part release when it burns? How is it going to accelerate the fire? The surface spread of flame, how easily does it burn? And then the smoke and the toxicity. So if we start by looking at heat release rate, and obviously a lower number is better in terms of heat release rate, the control, not surprisingly, has a very high heat release rate of 300 in terms of mare, which is the maximum allowable heat release rate to this standard. It isn't an FST resin. It's going to act purely as a fuel source and burn and liberate a lot of heat. If we look at the impact of incorporating that 0.5 millimeter layer of Technifier, we've improved that mare by 61%, the heat release rate down to 116. So we've had a significant impact on the amount of heat that composite part releases in a fire event. If we look at the requirements, these hazard levels to 45545, HL2, the mid-level, which we believe is going to cover about 60 to 70, 80% of trains, the MARE requirement is less than 90. We're at 116. We're not quite there, but a significant improvement from 300. And we're confident that through inclusion of a small level of a secondary fire retardant technology or additive would get us over the line for HL2. And this is the systems approach that Scott alluded to in his presentation. If we look at surface spread of flame here, a higher number is a higher level of performance. The control comes in at 5.9. The Technifire enabled panel offers 100% improvement up to 12. So we've significantly improved or significantly reduced the ability of that part to burn in a fire event. If you look at the requirements to 45545, they're very, very stringent. So all three hazard levels define a surface spread of requirement, a surface spread of flame requirement of greater than 20. So we're not there yet. We've got significant improvements from 6, but again, we're confident a small inclusion of a secondary fire retardant additive would push us forward. If we look at the smoke is really interesting. So that is an exceptionally high smoke level, 1,430. This is a styrenated orthophthalic resin, lots of aromatics. It's going to liberate a lot of smoke when it burns. And if you look at the requirements, that's outside of the requirement of the lowest level, HL1. So it's failed the requirements to EN 45545 completely. If we look at the improvement of incorporating the 0.5 millimeter layer of Technofire, we've got a 78% improvement. We've dropped that smoke generation down to 316. And if you look at the requirement for HL3, the highest level of performance, that's a maximum of 300. So we're right on the borderline of having an HL3 smoke performance here, going from a system that was failing HL1. And if we look at the toxic fume, the CIT, the control has a toxic fume at critical indices of toxicity of 0.28. That's been improved by 61% to 0.11. The HL3 requirement is less than 0.75. The base resin, although it's not FST, it doesn't contain any halogen or antimony, so it's not generating toxic fumes. But we're still seeing a 61% improvement. So if we look at that overall, if we look at the percentage improvement column, by dropping in this 0.5 millimeter layer of Technofire as a functionalized surface veil pre-vacuum infusion, we've improved heat release, surface spread of flame, smoke and toxicity by 60 to 100%. If we now look at the results from the mid-level FST resin, and this is exactly the same structure of the table. So we've got the heat release, the surface spread of flame, the smoke and the toxicity. If we look at the control, we've got a significantly better heat release rate compared to the orthophthalic resin in the last table. The ortho gave 300. Here we're down at 120. So as you'd expect, this is a FST performance resin, so we're going to see a lower heat release rate. But if you look at the impact of incorporating the Technofire, we've improved that by 88% and have dropped the heat release rate down to 14. That's one of the lowest heat release rates I've seen with a styrenated vacuum-infused composite panel. And there's obviously some interesting synergy occurring between the intumescent Technofire mode of action and the fire retardancy that's built into the base resin. And again, if you look at the requirements, HL3, the highest hazard level, defines a maximum heat release rate of 60. We're down at 14. So we've significantly improved the way that that composite panel performs in a fire and how much energy it liberates, how it feeds the fire. If we look at surface spread of flame, we're not actually seeing an improvement here. This is an FST resin. It's designed to offer very high levels of surface spread of flame, so not really surprising. And if we compare that to the orthophthalic resin that had the control, had a surface spread of flame of 5.9, here we've got 48, where a higher level is better. So not surprising, we're not seeing a significant improvement. And the HL1, 2, and 3, as we said in the last slide, all define surface spread of flame greater than 20. The smoke is interesting. The smoke is quite a poor level. It's not as bad as the styrinated orthophthalic resin, but it's 846. So it's in HL1, the lowest level of performance. And we've improved that by nearly 50% by incorporating that layer of Technifier down to 440. So we've got a really good mid-level HL2 performance just by dropping in that functionalized surface veil. And the toxic fumes you can see is very, very poor. We've got a critical indices of toxicity of 1.42. This is a halogenated resin. So as we mentioned at the beginning of the presentation, these systems work by liberating toxic gases that are very effective free radical traps, but are going to fail a toxic fume standard like 45545. And if you look at the parameters, that's outside of the parameters of this standard. But again, if we look at the improvement of incorporating the Technifier, we've improved that by 44% and dropped it down to 0.79. We look at the requirements, the HL3 requirement for toxic fumes is less than 0.75. So we're virtually on the limit of the highest level of performance to toxic fume standard with a halogenated system by incorporating the Technifier. And again, if you can loop back and think about the way the veil intramesus expands, forms that stable carboniferous char, it's preventing toxic fumes from getting out, fuel source from getting out, it's preventing heat and oxygen from getting into the laminate. So again, if we look at it overall, we're seeing almost a 90% improvement in heat release rate and a 40-50% improvement in smoke and toxicity by incorporating Technifier with an FST resin. I'm going to hand back to Scott now, who's going to pick up on some real-life applications where Technifier is currently used in composites, and we'll pull together a summary, and then we'll take some questions.
Thanks, Neil. Yep, just have it's 5 slides left, so 5 more minutes, and then we will field the questions. Technifier in the Whitestone Bridge project. This was a program in 2000. Well, it was finally installed in 2005. They looked at putting wind fairings on the Whitestone Bridge, composite wind fairings, and the designer used Technifier on the outside, really a reaction to fire, but they've also used an infusible grade on the interior of the panel. So it really hits both of the the purposes of our webinar, the fire resistance and the reaction to fire. So what I'd like to describe here is the outside layer was that pre-preg version that was held in place on the wind fairings using an SAB 3M product. So a peel and stick adhesive that is held up to this point. It's now 2022. It's 17 years into the project. The original design life was for 8 to 10 years. So we've basically doubled now the original life. They are replacing that section this coming, I would say, over the next 3 years, but the project starts again in the spring. So you might be able to, if you're driving through that part of New York City, you might want to look over and see those fairings and think, I do know a little something about that project. Next slide, please, Neil. Another past project involving Technofire was on the BART system in San Francisco. The train floors were not resisting impact. The phenolic panels they used at the time were becoming damaged. So they decided to drop Technofire in with a vinyl ester sandwich over a balsa core to replace those panels. And they did have to pass the Doc 90, the E162 and 662 that we discussed earlier today. I believe that's still in operation today. So if you have any more panel type programs, we do have some history behind there with different testing. Next slide, please, Neil. So different Technifier use in composites. We've seen the bridges. We've talked about trains and buses, also structural panels, and a lot of the architectural designs now are looking at facades. And after Grenfell, there's been kind of a serious overhaul on the design work and the test requirements. So we are active in those areas, as well as utility poles. We had highlighted that 18 months ago when we ran a similar webinar. That is still an active program. We have a lot of one-off past architectural structures and theme park rides. We've also looked at the military and non-military use of emergency shelters. And we do have Technifier that is flying on some airframes currently and are engaged in some current aircraft programs. Next slide, please, Neil. So some new developments we're looking at is to raise that higher initiation temperature up to a 280 C. We are very limited with what we have to offer right now on the 250, but we have the 280 C available to us. So we're looking for the right partner to run, to start a program involving those higher initiation temperatures. We're also designing lighter weight and thinner variants of Technofire. The thinnest version we offer, that 0.25 millimeter thick one I mentioned earlier, that's on a glass backbone, a glass fiber backbone. The thicker versions, the 0.5 and up, are based on a high temperature fiber backbone. So we are looking at some chemistries and different types of components on the market. We're very active. There's about a 40% internal research and development program that we hold at TFP. So a lot of our activity is designed towards incorporating these new flame retardants that are hitting the market. So we work with a lot of partner companies, who are producing these chemistries. And I'm active in the PINFA NA group as well. That is another source of a lot of those components that you probably have seen on the market. So we're active right now. We've looked at about 120 different chemistries, FR chemistries, and incorporate into our veil. It is a wet laid process, so we're not looking at solvent use. We've also embraced the systems approach, incorporating Technifier with these established FST resins and a variety of the FST resins for increased performance or reduced weight. Again, we like to stay very active with resin manufacturers and see what's new on the market and try to test those. Next slide, please, Neil. So in conclusion, Technifier is offered in a large variety. So we have, like I said, different thicknesses, particles can be added, different forms. We've looked at adding an adhesive layer onto the pre-preg version. So whatever needs to be done to carry this, either carry your product or to act as an active surface into a composite application. We consider it more of a drop-in solution. Nonwovens are very common in the composites industry because of their ability to soak up resins or to be very flexible for different components. There's some shielding properties that are attractive. So we are just another nonwoven that can be dropped in as opposed to an exterior coating after the initial build. We want to be built into your composite. We want to be there from the beginning of the formation of your composite. So we look at Technifier as a solution in the fire resistance and reaction to fire composites industry. It is suitable for a variety of standard composite fabrication techniques, and also those different resins. And we're also looking to reduce the weight. I mean, that's a lot of what composites brings. To me, the elephant in the room in composites currently, and I'm biased, but is the fire protection component. These are petrochem based materials that are commonly used. So they're based in oil. They love to burn. So how do we stop that, or how do we create enough time for people to escape a scenario, a fire scenario? That's where our mission is in Technifier. We would be very willing to discuss any programs you have, and we always look to partner up with people with the right business case. As my boss always says, is it real? Is it worth it? Can we win? So we would just evaluate just to not waste your time or our time, but we are, once we're on board, we are kind of a relentless partner. We have a lot of Technifiers that only have one customer. So we developed it only for one specific use, one specific program. So we're open to hear from you and to learn more about your programs to see how we can help. In closing, I would just like to thank one of my PINFA colleagues, JP Schroeder at Scott Botter, for his help on some of these programs. And again, to CW for hosting this and always offering good content into the Composites World. Thank you.
Thank you, guys. That was great. We're low on time, so let's get right to our questions. We have quite a few. How is this product different from inorganic reinforcement mats, for example, glass fiber, as they do not catch fire?
That's an interesting question. I'm happy to pick on that one. We take glass fiber in some of the Technifier products we have, but we then incorporate the specific grades of intrumescent chemistries that give us that char formation ability. So glass fiber itself won't burn. It'll melt when you're getting up to 400, 500, 600 degrees C, but it won't give you that stable char forming ability that Technifier has.
We also, Neil, the high temperature fibers that we use as the backbone in place of some of the glass fibers would withstand, instead of 700, 900 F, when you start to soften your glass fiber, you're talking 1500 F on some of these fibers. So it's a more stable thermal fiber.
Next question. Is there any work being done for aircraft interiors, for battery enclosures for the aerospace industry? Didn't you reference some of that? Have you done some prototyping?
Yeah, this is an absolutely booming growth area. EV overall, there's a beautiful little statistic. If we look at cars, that in 2019, 2.5% of all cars were EV. That's going to grow by 2029 to 25%. So the whole EV battery area is developing very, very rapidly. The standards are developing in real time. So the kind of lead standard at the minute is the new Chinese bonfire test, the GBT 38031. And we're quite heavily involved in several projects looking at the value that Technifier intumescent veils can bring. One of the key advantages that the designers like about Technifier is that they can still retain use of a high performance epoxy prepreg material or a toughened epoxy resin and drop in the Technifier as the thermal insulation product or the FST product. They're not having to go to a heavily filled FST resin or a phenolic or a PFA resin, which tend to be very brittle and give lower mechanical performance. So they can achieve the high levels of mechanical performance from the resin whilst achieving the necessary FST or insulative properties from the Tecnofire. And we were involved in we gave a Composites World webinar on EV batteries and the application of Technifire and the application of EMI shielding veils. So if whoever is asked the question, if you'd like to contact us directly, we'd be very, very happy to share that link and have a further discussion.
Can you give any comments on electrical or thermal conductivity of the material?
Sure, I can speak to the electrical conductivity side. I saw you freeze, Neil. I'll take that one. Electrically, because there are some graphite components, but they are not necessarily in contact with each other. So we consider it a non-electrically conductive material. Upon expansion, the density is so much lower too that we don't consider that post expansion to be a problem as well. But what was the second part of that question?
It was electrical and thermal conductivity.
Right. Well, thermally, that's very subjective, right? But as a mat itself, pre-expansion, we don't consider it because these are very thin. They're not considered high insulators in a sense, but in terms of the thermal abilities, that's what that char layer is trying to achieve, right? Is to gain that false wall, that layer that is going to add to the thermal conductivity, or really thermal insulation value, I should say. It's not going to conduct heat through it quite well. We're trying to design it based on is your test 15 minutes. They think it's 15 minutes to survive a fire event. Then we'd have to look at how many layers of Technifier maybe, or just a thicker version to get to that. But we are aware that the thermal conductivity or the thermal insulating values are very important when you talk about fire resistance. And we have had some luck with some of the headier tests. The NFPA 285, for example, is one of those, and some E119 tests in the past as well.
We have recently, just to pick up on the electrically conductive question, we have recently generated some data in this area because there tends to be an assumption, because these materials contain graphite, that they are going to be electrically conductive, and people are concerned about that, especially in the EV battery applications. Essentially, they are insulating. There isn't a conductive pathway through the material, so we do have some data we can share on that. So again, if the person who asked the question would like to contact us, I'd be very happy to share that data.
Is there a version of these veils that can be cold bonded onto a CFRP laminate or surface post-cure, after the cure, or do they all need to be co-cured?
Well, I think the example of the Whitestone Bridge program, where they took that prepreg type Technifier, the veneer type, with that 3M adhesive and adhered it to the surface, that creates a very, very strong bond. So I think that would be the solution in that case. In some of the cases we've had where they formed, their processing was well above a very high 280C. So we've had to use that as an alternative to get the product onto the surface. Or retrofitting. Let's just say you had a fire event and you had a panel that contained our Technifier. That expansion is irreversible. So once it expands, you'd have to try, basically knock out that portion that was damaged and replace it, where you could then look at maybe that peel and stick material at that time.
All right, I'm going to push on with 2 more questions, then we're going to wrap it up. Are the veils repairable if damaged in service? Chips, gouges, scratches, punctures, etc.
I think that's kind of where I was just ending that last question. Once it expands, you'd have to replace it. And then we would look at some kind of a retrofit, which we do have a little bit of experience with. So it would come down to kind of a scrape and fix at that point, and try to reestablish the layer of Technifier that's required onto that surface.
But if you just damaged it in service, can you repair it? It hasn't been burned or anything, just chipped in service.
Sure. Again, we would probably look at what resin system was used and see if you could emulate that original formation of the part, or look at this pre-preg version of the Technifier.
Yeah, I think one thing that is worth saying is, in comparison to an intrumescent coating or a paint, which doesn't become an integral part of the composite, which is quite easily damaged, the majority of composite applications for Technifier, the Technifier is used effectively as a functionalized surface veil. So it becomes an integral part of the surface of the composite. So it's much, much more robust and durable than a paint or a gel coat.
And then finally, what is the status of certification? Are these ready to use in applications?
Well, we're not listed per se like a true systems product. We're kind of a component. So we'd certainly be open to that discussion later. Is there a test? We've always kept in the back of our mind, is there a UL listing we should go after? Is there? But the variety of applications we haven't found one. We haven't landed on one yet that makes sense in that respect. What I can say is we have a lot of history of passing tests on a third-party level, so I can't share a lot of that data, but we could say, yes, we have passed NFPA 285. It's not listed in the IBC anywhere. But intumescence, I think as the composites industry grows, that will also change. If you look at the work from IACME and some of the other organizations out there that are trying to establish composites in the IBC more, we probably will find one open up then. But as it sits now, we don't have a true listing per se. That makes sense.
I think there's also talk in IACME of doing several databases for aviation and urban air mobility. So I would imagine that would help as well.
Sure. I mean, we're all here trying to move composites forward, right? So we're certainly part of that community, and we feel like fire protection is one of the keys. But like I said, I am biased.
Well, thank you. And I would encourage everybody that's interested. We couldn't get to all the questions, but I know Neil and Scott will work to get those answered for you. And please do reach out to them. We really appreciate both Neil and Scott and TFP for all they do. And we appreciate all of you, our attendees today. We hope to see you again soon at the next Composites World webinar. Have a great day, everybody.
Thanks, everybody.
Thank you.